Hello, welcome back to the short lectures in physics. Topic for discussion in this session is total internal reflection of light. We know in reflection, a light ray that strikes a smooth polished surface at an angle of incidence returns back into the same medium in different directions. Whereas in refraction, a light ray deviates from its path as it travels from one medium to the other with the different refractive index values. In this, the product of refractive index into sine of angle of incidence remains same for a medium. Mu sin I is constant in refraction, whereas in the reflection, angle of incidence is equal to angle of refraction. And in refraction, when a light ray passes from a denser medium to a rarer medium, the light ray is known to refract more and moves away from the normal drawn at the point of incidence to the rarer, denser medium boundary surface. Thus, the angle of refraction is more than the angle of incidence. Light rays gets emitted from an object placed at the bottom of a denser medium in different directions. The rays reach the denser rarer medium boundary at different angles of incidence. That means the angle of incidence keeps increasing with the inclination of the ray coming from the object to the boundary. As the value of angle of incidence increases, the value of refraction also increases. In the process, for a particular angle of incidence, the angle of refraction becomes 90 degrees. This angle of incidence is known as the critical angle of incidence. That is, the critical angle of incidence C is the angle of incidence for which the angle of refraction becomes 90 degrees in the other medium. For values of angle of incidence greater than the critical value, that is, angle of incidence I is greater than C, the critical value, then the refracted beam do not enter into the rarer medium but reflects back into the denser medium itself. It follows reflection principle under these conditions. In this slide you can see the object is placed at the bottom of the water tank O, and light rays are getting emitted from that in different directions like the rays shown OP, OA, OC, OE, OX, etc. For each ray, the angle of incidence increases from 0 degrees for the ray OP to higher values for the other rays. As shown, for the ray OA it is theta 1 and angle of refraction is theta 2 at the point A, and at the point C it is theta 3 is the angle of incidence and theta 4 is the angle of refraction. And for the ray OC, the angle of incidence becomes critical value, that is C, for which the angle of refraction becomes 90 degrees at the point E, and the refracted beam travels along the water level, that is water air boundary level surface, as EF. And if the angle of incidence is further increased, that is for the ray OX, then the theta I is more than the value of C. Hence, the ray OX reflects back into the water medium, that is the denser medium, back following the reflection principles. Here, theta A is the angle of incidence at the point X, and theta R is the angle of reflection, such that theta A is equal to theta R. So, this phenomena in which the light ray totally reflects back into the denser medium and it travels through a denser to rarer medium boundary at an angle of incidence greater than the critical value is known as total internal reflection of light, like the ray OX. In this situation, the boundary surface separating the denser medium and rarer medium acts like a smooth reflecting surface like a perfect mirror. And it may be noted that there will be no loss in the light as the total light gets internally reflected, unlike in reflection, where some portion of the light may get absorbed in the mirror material and the rest is reflected back into the medium. It should be remembered that for total internal reflection to take place, the light must travel from a denser medium to a rarer medium, and the angle of incidence at the denser to rarer medium boundary should be more than the critical angle of incidence for a particular denser medium. Relation between the refractive index of the denser medium, for example in this mu for water, and the critical angle of incidence C is obtained as follows. According to Snell's law, mu sin I is constant. So mu of water into its angle of incidence is C sin C. So mu W sin C is equal to mu A into sin 90 because angle of refraction is 90 degrees. Hence mu W sin C is equal to mu A sin 90. Mu for air is 1, sin 90 is also 1. Hence mu W sin C is becomes 1 or mu W is equal to 1 by sin C. So for an unknown medium, its refractive index can be obtained by measuring the critical angle for the denser medium. Or the critical angle C is given by sine inverse of 1 by refractive index of the denser medium, that is mu water. Let us see some examples of total internal reflection we see in day-to-day life. The diamonds, when we see, it sparkles and with a very bright intensity of light within the diamonds. The brilliance seen in the diamond is also due to total internal reflection. The refractive index of diamond is 2.47. So the critical angle, that is sine inverse of 1 by 2.47, that becomes about 24 degrees. So for diamonds, the critical angle of incidence for the light to be contained within the diamond material is about 24 degrees. And the diamond faces are cut in such a way that light traveling through a diamond reach the diamond air boundary at an angle more than 24 degrees. As a result, all the light rays undergo total internal reflection at all the boundaries. This sort of multiple total internal reflection make the diamond appear more bright with the sparkles when viewed in the direction of the emerging light. From any surface, if you see the diamond, it sparkles. This is the total internal reflection is the reason for this brilliance is seen observed in the diamonds. Another example is mirage experienced in deserts on a hot summer day is also due to total internal reflection. In the slide you can see there is a desert land and a person is watching an object PQ from a distant point O, and the light rays from the top of the object P travel in different directions towards the observer. Being summer, the temperature in the different layers of the air above the ground varies. Because of the sand, heat will be absorbed more, so that air zones close to the ground surface is very hot, that is hot air zone. As you go slightly above towards the top of the object, the air becomes relatively cool. That means there are different layers of air from the ground to the top of the object or above the surface of the ground with varying temperatures, being hot at the surface of the ground and cool at the higher heights. So this is indicated as hot air zone at closer to the point Q and cool air zone at the point top of the object P. In between, the temperature decreases as we move from the point Q to P. Due to the temperature variation in different layers of air above the ground, the respective density and the refractive index values also vary. Density and refractive index values increase for zones lying above the ground. That means the refractive index of the hot air zone is less as compared to the cool air zone at the top of the object. So a ray of light coming from the top of the object travels from a denser medium to rarer medium as it passes through different zones of air layers as it moves from point P to the ground surface. Thus, it moves away from the normal. At a particular position like point S shown in the slide, the angle of incidence becomes more than the critical value for that particular hot zone that results in total internal reflection. Under such conditions, the ray of light reflects and returns back into the same medium, that is into the cool air zone from where it enters. When such reflected ray travels in the same direction and reaches the observer, he feels that the ray of light is coming from a point R instead of from point P. So this makes him to feel that he is observing the inverted image QS of the object PQ in the pond of water. So it is an illusion created to the observer due to total internal reflection of light. Now we can see because of the total internal reflection, the light passing through a right-angled isosceles triangle can turn through 90 degrees and 180 degrees. Let us examine these situations. Consider a right-angled isosceles triangle shaped glass prism ABC as shown in this slide. Its right angle is at the edge B such that AC is the hypotenuse and the equal sides are AB and AC. Let the light rays enter the prism material from the side AB with an angle of incidence 0 degrees, that is normal incidence, like ray PD and RE like that. So as it is entering at 90 degrees, the light ray travels straight from P to D till it reaches the hypotenuse side AC at the point D for the ray coming from point P and at the point E for the ray coming from point R. As it touches the hypotenuse side AC, they get total internal reflected because the ray is incidenting at the surface AC at an angle of incidence 45 degrees as shown with reference to the normal drawn at the point D and the point E. So the both rays coming from P and R, normal incident rays, they meet the side AC at points D and E with an angle of incidence 45 degrees, and it may be observed that the critical angle of incidence for the prism material is about 42 degrees. Because the angle of incidence 45 degrees is more than the critical value 42 degrees, rays PD and RE undergo total internal reflection. Thus, they turn back into the prism material as rays DQ and ES. This makes the incident rays PD to turn 90 degrees through and emerge out the prism material through the base BC as ray DQ, and similarly the ray RE turns through 90 degrees and emerges out as a ray ES. So this total turning through 90 degrees is because of the total internal reflection. Same prism if we put in a different way as shown in this slide, such that the light ray from point P enters the prism material from the air medium as PQ and meets the air glass boundary surface at AC. The angle of incidence is again 0, so normal incidence. So the ray PQ enters the glass medium straight and meets the glass air boundary surface at the point R on the side AB. AB and BC are equal sides. Because the angle of incidence for the ray PQR is 45 degrees, which is more than the critical angle of incidence for the prism material, that is 42 degrees. Hence, at the point R, the ray PQR also undergoes total internal reflection so that it reflects back into the prism material with an angle of reflection 45 degrees. The ray RS proceeds in the prism material as ray RS till it meets the glass air boundary surface BC. At the point S, it meets the side BC at 45 degrees angle of incidence. Hence, which is also again more than 40 degrees the critical value. Again, it undergoes total internal reflection and reflects back into the prism material at the point S shown as ray ST. As it meets the glass air boundary surface AC again at point T, it again, because the angle of incidence is 0 with reference to the side AC, it leaves the prism material and travels straight as ray STU. So in the process, the ray started from point P reaches point Q through total internal reflection occurring at points R and S. The total angle of turning is 90 degrees at the point R and 90 degrees at point S. Hence, the ray coming from P turns through 180 degrees and reaches the point U. So this is also an example of the total internal reflection. The other application of total internal reflection phenomena is optical fibers. They are designed based on the principle of total internal reflection. An optical fiber is a transparent cable used to transmit light from one of its sides to the other end through multiple total internal reflections of the light within the fiber material. It consists of a cylindrical core made of long, extremely thin strands of high quality glass or quartz material. Approximately, its diameter is about 8 to 12 microns, that is 10 to the power minus 6 meters. It is covered circumferentially by a cladding of different glass material having refractive index value lower than the refractive index value for the glass core material. Approximate dimension of the cladding is about 125 micrometers in diameter. Because of the differences in the refractive index of the core and cladding materials, the total internal reflection of light rays entering the core at one end takes place. In this figure, you can see light rays entering the fiber optic core cable in different directions and entering into the core material. The core material is having higher refractive index value as compared to that of the cladding material. And both the core and cladding is protected by another plastic jacket to avoid any possible damages to the core glass material. Also, this enables the cable to be bent in any direction for easy use. The rays entering the core material in different directions will meet the core cladding boundary surface at different angles as shown in the figure. Till the angle of incidence reaches the critical value for the core material, the light rays get refracted through the cladding material. For angles of incidence more than the critical value for the core material, they get total internal reflection because angle of incidence is equal to angle of reflection, they undergo multiple reflections inside the core material for all the rays entering into the core material, as shown in the slide. Majority of the light entering into the core material will undergo total internal reflections and then leave the other end of the core material as shown. That is total internal reflected beam. The light entering the optical cable thus gets confined to it. The light rays entering at some angles of entry, they strike the core cladding interface in different angles of incidence. For few of them, the angle of incidence become more than the critical angle. So those rays experience total internal reflection. In other words, only the light ray that enters the core within certain range of angles of entry can travel through the entire length of the optical fiber through multiple total internal reflections. This range of angles of entry is called the acceptance angle or acceptance cone of the fiber. Acceptance angle is a function of the difference between the refractive index values of the core and cladding materials. As a result, there exists a maximum angle alpha as shown in this slide from the optical fiber axis that allows the light to enter the fiber and travel uh, through its entire length. Sine of the above maximum angle is called the numerical aperture of the fiber. So from the figure you can see alpha is the maximum angle of entry for the light rays to enter the core material and undergo total internal reflection throughout its length of the cable. I is alpha. So the numerical aperture is given by sine alpha. The optical fibers are designed in such a way that the total internal reflection of light occurs even in case the cable gets bent. Optical fibers are used in medical applications as an endoscope used to study inside details of stomach and intestine. They find the use in transmitting images of objects like in televisions, broadcasting and telecommunication applications. They are also used in transmitting electrical signals from one place to other without any loss in signal strength for defense and aerospace applications. Also used in imaging places that are hard to reach in industries. They are also used in safety measures like airbag controls in our cars and lighting purposes in automobiles. Hope this finds useful to you and see you in the next session with some other interesting topic. Till then, bye.